Hi, and welcome to another Hopper video about reliable computing with microcontrollers. It's been a little while. If you've watched my other videos, you're familiar with my garage door project that involves sunset lights, knowing when the door's open or not open, ambient light, knowing what the time is, and trying to make devices that basically run forever. My current record is 8 months without needing to do anything to it. Obviously, I'd like to get it a lot longer than that. So the latest one's been running for just over a month, and that's this one here. So inside, it's got a full-size Feather microcontroller, and you can see the edge of another board here. That's the radio board. So it's a HC12 radio board, which is 433 megahertz radio, which behaves like a UART, like a serial port. And it's got some LEDs and a button. And I've 3D printed this case so that you slot the board in. This slots in on the other side of the board, and it all just sort of sticks together. This board slots in there as well, and these are sort of force fit LEDs. But I then got a request from a friend when he saw what I was doing with my door that if I could put door sensors on his doors in his work environment. And the way mine looks in the garage is a little bit Heath Robinson, because I've got multiple peripherals that he doesn't need. So I've got a relay to drive my driveway lights. I've got a real-time clock to know when sunset, or to know when 10 p.m. is. I use an ambient light detector to detect sunset. And then at 10 p.m. I turn the lights off. And if you open the garage door in the early hours of the morning, like you're going to the airport or something, it turns the lights on, the driveway lights for a little while. And this is the HC12 radio, but obviously, to scale this up is going to give me more work than I'd like, and also reliability issues. So having done this for a little while and played with these various different devices for a little while, I decided to make a generic PCB. So what we have here is a PCB that's designed for a tiny version of a microcontroller, specifically the Pomeroni one. And it's got female headers on it here, but it doesn't need them. And it's got support for 3 different LEDs, each with a current limiting resistor. You could convert these to digital inputs if you just put a jumper across here, a 0 ohm resistor, then you could use them as inputs as well. But I don't need them as inputs usually. So I've got 2 digital inputs and 1 analog input. So my ambient light detector, for example, is an analog input. These could be inputs or outputs. So I could drive a relay with one, or I could have a door detector on it, or whatever. And then I've got female headers on this so that I can use it experimentally, so I can plug the devices in and out. I can plug LEDs directly into the headers as well, like that, just for quick prototyping. As a convention, ground is always on the right. So the right-hand pins of these sensor or activator, so it's always ground on the right, or ground on the right of the LEDs. The next pin across is the positive voltage, so 3.3 volts, and then the next pin across the left is always going to be the signal pin. And that's based on the convention of the fermion and gravity sensors that you can get from DF Robot, which I really like because they're kind of industrial and they never fail. They're not dinky little devices. Anyway, I made myself a bunch of these boards, and I'll put a link in the description to where in the Hopper repo you can find the Gerber files to print your own if you want some. This is what I use for a power supply, or some similar thing. Super reliable to just get your power directly from USB. These are the door sensors I've got. Again, these are gravity sensors from DF Robot, 3.3 volt capable, and they've got a little screw you can adjust in the back to adjust them sensitivity. They're infrared proximity detectors, and you can adjust them to be anywhere between 0 and 200 centimeters. 0 meaning like, you can put your hand right in front of it, and then 200 centimeters being 2 meters. But I use about 20 centimeters, so I make it so that the door will slide past less than 20 centimeters from the device. These are 3D printed brackets for them. And you can see their color coding is is the same convention as my pinout. So it's ground on the one side, then the positive voltage they've got as a brown, and the signal they've got as a blue. It's the same for the other detectors. Okay, so my friend who's his cabinetry making workshop, in his main workshop he wants the sensors, and then he's got 3 doors that he can't see from the workshop and he wants to know whether they're open or not. I use this tiny 2350 from Pomeroni because, well, it's small. Also, it's got a USB-C, which is far preferable to the older ones, and it has a built-in reset button. To me, those are 2 minimum requirements of one of these RP2040 or RP2350 microcontrollers. The tiny 2040, the previous version, has the same pinout. It just doesn't have this stemmer connector on it. So the pins are the same. And then on the PCB, I've marked which GPIO pins and which analog pins. The radio is hooked up directly to the default UART pins, which are 0 and 1. And 2 is used for the set pin, which is used to put it into configuration mode. And later in this video, I'll do a little software demo so you can see what I mean by that. 3D printing the case. So the covers for the cases are printed transparent, and these are made so that if you stick an LED in it, it sort of force fits quite well, so you don't even need glue to make it reliably stay in there. You know, by reliable computing, I mean if the thing works today, it should work tomorrow. You shouldn't have to go, have you power cycled it? You know, have you tried turning the power off and on again? Or you shouldn't need to update anything ever. If it worked yesterday, it should work tomorrow. Okay, building up the sensors for, so here I've got 3 different doors. So I've marked them left, middle, and right, just to keep track, because the program's slightly different on each microcontroller to send a different signal for each door. So they're sending the signal on the same channel. And each of them has a single LED so that when you're in the garage looking at them, you can say, what does it think the door is right now? And that'll show green if it thinks the door is open. And I'm only using a single pull-down resistor, a current limiting resistor, and a single LED, or one of my GP pins for the LED. I'm using a single input, and it's a digital input from the proximity detector. And there's a slot here in the case where that cable comes through. Everything slides together, so the board slides into this blue part, so it sits there snugly. It's quite a tight fit, so it doesn't move. And then this cover slides on to the top here, and that so there's no gluing of anything. There's no screws necessary. These are for the mounting screws. Okay, let's carry on. So another view of the same thing. So you can see how it's not much different to the previous view. This is this is a sensor with with the door detector, and this is the monitor which sits in the workshop so that they can see 3 lights for left, middle, and right door being open. And so it's got 3 current limiting resistors and 3 LEDs, and these are beautiful blue LEDs. The actual LED when it's not lit is transparent, but they're super bright blue LEDs. Yeah, and then we've got my HC12 radio module and the tiny 2350. And I'll show you where these come from and what they're all about later in the video. So that's what it looks like when one of them's lit up. So right door is open, for example, and that's where the power supply is coming from, USB-C. Right, so this little demo video shows you, obviously they're right next to each other, but the link between these is radio. So they detected something in front of the right-hand one. The right-hand light went on, and then the middle one. Slight delay because I'm not swamping the radio channel with signals. I'm only doing it when something changes. So there's about probably a 1 second delay between sensing whether something went in front or something went away. There you go. I'm using some form of USB power here. So in my case, I had to put something in that would feed through the main power because I'm putting them in the same socket as the door opener. So it needed to have a power socket as well. Anyway, that's them in operation in test mode in my on the floor in my workroom. And this is what it looks like when one is installed in the garage. So this goes to the power socket of the garage door opener. And then you can see the bracket I've put in here to put the sensor sort of within 20 centimeters of where the door would be when the door's open. it's that simple to set up. And then this is the sensor side, and then the monitor side, which is in their workshop, has this on the wall where they can just clearly see if one of the doors is already open, because they can't see the garage doors from where the workshop is. Right. And I think that's all I have for these. So now let's go and look a little bit at the technology. What do we got? So yeah, this is the microcontroller I'm using. I'm in New Zealand. I'm getting most of my stuff from Little Bird Electronics in Australia. So the microcontroller I get from them, and also the radio module. So this is a UART radio. So it makes the radio behave like a serial port, like RS-232. So, you know, baud rate, parity, all that sort of thing. So it's super easy to send signals across from one to the other. And then the sensors I'm using, this is from the gravity range from DF Robot. This is the sensor, and it's you know, it can work in 3.3 volt or 5, and it's adjustable between 0 and 2 meters basically. And I set it to 20 centimeters or 25 roughly there. And then the other sensor that I mentioned is I also use their ambient light detector, which is an analog sensor. Yeah. And it's pretty darn decent too. I've done a lot of experimentation with these. There's other videos on the channel that talk about it. Let's go back to the Tiny 2040. This is the pinout. So the difference between the 2350 and the 2040 is they added this connector at the end here. So I'm breaking out an analog signal. 0, 1, and 2 are going to the radio. So 0 and 1 are the UART default. And 2 I'm just using as a digital signal to switch the radio into configuration mode. And then I'm using the remainder of these GPIO signals for the LEDs and for the 2 digital inputs. Right, I think that's enough of that. Let's just go and have a look at the stuff in person. So that's the little board I built with my hand to scale. You can see it's nice and tiny. And you don't need to use it with the radio. You could just use this for just to mount a Tiny 2040 or Tiny 2350 and have input and output, you know, like at least 3 LEDs and some. So for an experimental board, much simpler to use than trying to use strip board or perf board, yeah, to build an actual project that's, you know, that you're trying to deploy. And then, yeah, the next level up you can do on that is to put female headers on it so that you can remove the pieces and not make it permanent. So put some header pins on rather than attaching things directly. And then if you do that, you can mount your 2040 and your radio in the header pins like that. And you can actually just mount the LEDs directly into the header pins since they've got their current limiting resistors on the board. So I'll show you how I'll do some programming later in the video with this one. Let me just show you what the sensors look like as well. So this is the proximity detector from DF Robot. These detectors are designed for industrial use, like in, you know, assembly lines. So they're super reliable and very accurate. It's, you know, it's probably got its own little microcontroller in there because you know, it's got its own little LED on the back to tell you whether it thinks it's been triggered or not. That's the little shiny thing on the left. And then it's got a screw in there to adjust the distance. So it's very easy to calibrate. You don't even need your microcontroller. You just plug it into the power and calibrate it by turning the screw until the light goes on where you want it to. So I really love these little devices. Super easy to use. Right, and then what else we got here? So this, I've got another one of those ambient light detectors. So that's the ambient light detector. And again, it has the same, they've got the same convention for the wiring for all their one-wire sensors or appliances like relays and things. So they've got, you know, power is black and red or black and brown, and blue is usually the signal wire. So really nice convention. And like I said, on my boards, the right hand, when you look at it from this orientation, the right hand pin is ground on all 6 of those connectors. Yeah, and then this pin here is just to stabilize it. It's a non-connected pin, yeah, whereas the ones on the other side are connected. Okay, so time to do some programming. So let's do that. All right. So I've got a little demo program here. Let me plug it into the power to just play with the LEDs, just to show you can do just about anything with this thing. And you see those lights come on. Like when I first plug this in, it turns on the RGB. You can see it's blue there. And that's the Hopper runtime booting up. Because it by default assumes that the built-in LED is active high, and in this device the built-in LED is active low, so I've had to write this little function to turn them off in case they've been left on. So set the three pins for the RGB LED. Let me show you where that is. So the RGB LED here, it's got 3 pins, 18, 19, 20, but it's active low, which is a little bit goofy. So it means that I just write a little method just to ensure that it's off. Turn them all to output, turn them all to true, which means off. So the first thing I do with these boards is turn off the built-in LEDs, because it can be a bit distracting having this little LEDs on for no good reason. And it's nice to have 3 of them because you can treat them as separate LEDs, so you can use them for diagnostics. Anyway, GP5, 6, and 7. And if we look at the board, 5, 6, and 7 are the LEDs. Yeah. So what's this program going to do? We say uses this board, and if we use that board, it defines what those pins are. So, you know, what pins are what. That's why you use a board. And now you can just use them. You can say make them outputs, set them off by default, and then we'll cycle through, turn 5 on, turn 5 off, wait, you know, after 500 milliseconds. Turn 6 on, wait 500 milliseconds, turn 6 off. I've actually got these the wrong way around, don't I? So, no, they're active low. Active low. So that should be false. And these should be true. Oh no, sorry. These are my LEDs, not the built-in LED. My LEDs are the correct way around. So true is turn it on, false is turn it off, true is turn it on, false off, true off. Okay, so now we can build by pressing F7. All the shortcuts are on the menus. So F7 was build. F5 would be launched in the debugger. So if we look at the bottom of the screen, successfully uploaded. And then if I just F5 to run, there we go. So we're cycling through the LEDs. You can see my LEDs like cycling through here. Okay, first demo showing how you use the board. Right. Next demo, let's configure which channel the radio is on. So Control C, exit out of there, exit out of there. And I've got this config program. Again, I'm telling it which board I'm using. I'm telling it what the set pin is, GP2. And it's going to just assume that the radio is on the default UART. So if you go UART setup, and we right click on that, right click to go to the definitions, it's using, it's going to call this setup with board overload, and it's going to use these pins for RX and TX for the UART. And as I said earlier, they're pins 0 and 1 by default on this board. So I'm using pin 0 and 1 for the UART, and pin 2 is the set pin over here, pin 2, to put it into configuration mode. Anyway, the source, the config source is checked in. All the source for this stuff is under source samples, MCU, HC12. HC12 is the name of the radio. And I know that my door sensor here at home is on channel 1. So I'm going to configure this to, because once you program this radio to be on channel 1, you only have to do it once. So I only have to do this setup in the configuration once, which is why I do it in a program of its own. So if we build this, see how red LED is still on, it's going to stay on. Because I'm not telling it to turn off. Like, load up this program. And now we just run it. So the first thing it's going to do is read the current configuration. and it looks like it was already on channel 1, and it's going to set channel 1. So it's setting the baud rate to the default. It actually isn't changing anything except the channel. So if I did something like changed it to, say, channel 42, I think it's 1 to 100 channels, and they're little sub-frequencies of 433 megahertz. So now if we run it again, this is the serial port, by the way, connection, the USB port connected to the computer. So now we've set it into channel 42. So if I, just to show you, if I power down and power up, okay, and now we F5 this again, load it up. We should see now that it is, even though I power cycled it, the radio should still be in channel 42. So F5. So yes, if you look here, it was in channel 42, and now I've set it back to channel 1 because my household system's on channel 1. Right, so we've configured it. Now, I've got another test program here, this Pico 43RX. Again, set it to the Pimeroni board so that our pins for UART are the good defaults. And LED pin, oh, it's going to turn this LED on and off when it's going to write that out. It's not going to go anywhere though. How is it putting this on the screen? RX. Oh, serial write char. Okay, so if I write this, now I have a device and I have the door open right now, which means every 10 seconds or so I'm getting the word open being transmitted across channel 1. So let's see if to the sensor device in my house, but that doesn't mean anybody else can't see it. So let's see if this device can see the same signal on channel 1. So if we F5, we're going to have to wait 10 seconds. There we go. And the word open just popped up there. So every 10 seconds, it's going to get a signal that says open. And I'm going to take a walk right now and go and hit the garage door open button. So it should send closed once, and then it should stop sending open. So I'm going to take a walk out the room and go hit the garage door button open. Yeah, the door is one of those ones that has kinks in it, so it gives a couple of these different false versions of open and shut as the door goes down, and then after the very last one should be shut, and then no more after that. And there we go. It stopped sending signals because I shut the door. There you go. In a nutshell, you've seen 3 demo programs of how to use this board, and one of the key things is it's for making remote sensors and to make them super reliable so that, like I said, you don't have to ever power cycle, you don't have to ever update. You're plugging it into a regular USB-C power source, and you've got a range of about 100 meters between your sensor and your monitor. Or switch, you could do remote switches as well, pretty much do anything with it. So I like the idea of having built a generic prototyping board that can be used for lots of different projects. And thank you for watching. If you enjoyed this kind of content, hit like and subscribe. Cheers.